Okay, sorry, some delay. Thank you, Kami. I'm Liao Yan. I'm working for the Nilaro support and solution engineering team. So, in this today's session is about discuss the postmortem debugging techniques in Linux kernel. So, firstly, we were to go through 3 techniques. The first one is the RAM ops, based on the software tracing for the postmortem kernel debugging. The another 2 based on the Coresight hardware assist tracing. So we can see on the right side that why not using complete? So on the right side we can see that if the system hung, then the kernel where to boot up relies on the watchdog timeout. So it were to for the kernel second time boot up, then we can rely on the RAM ops to get out the trace data. So this is based on the software method. Then on the right side we can see that there have 2 methods. One is based on the Coresight CPU debug. So for example, the CPU hung, we can read some information, CPU state from the Coresight CPU debug module, or the kernel panic, or also can read out the CPU debug unit information. Another method is that we can rely on the kdump and the crash tool to recovery the Coresight tracing data, and finally we can based on the perf plus open CSD to decoding the tracing data. So this is the general information. So we will finish this material plus 3 demos in 25 minutes. Okay, so we can see the first one is that if we want to find the program execution flow for the system hung issue. So after the system hung, usually we cannot rely on the console because they have no response in the system. Another thing that modern CPUs, they have the improve the performance. So they have many async operations on the bus or the DDR controller. So for example, early acknowledge or the auto forwarder and so forth. So such kind of the system that may not hang immediately after they have the bad instruction. So for example, the CPU system is stuck. So we connect the JTAG debugger on it, so we can check the PC value. But actually this PC value is not really the bad instruction. Maybe they have run for where. So for this case that we need to narrow down the course. We need to reverse the program execution flow to find the hints. So in Linux kernel, there have one software mechanism, RAM ops. Usually we also call it as pstore. So it's a general framework based on the persistent RAM. So after the boot restart, the persistent RAM can be preserved. So we can get to know the last time some of the debugging information from the preserved memory. So RAM ops can dump, for example, the console message, ops and panic log, and the last thing is that the function tracing. So RAM ops function tracing we can use to reverse the program execution flow. So basically that I want to demonstrate the demo is that the steps is we need to enable that in the kernel building. So we need to enable the pstore and the debug FS. And we also need to, after the kernel booting up, then we need to, based on the debug FFS, so we need to enable the RAM ops, the function tracing, use this command. And we also, because that the system hung, then we need to use the watchdog to reset the boot. So after that, then if there have run some case and the system hung, after the second time the kernel booting up, so we can, based on the pstore virtual file system, and to get out the tracing data. So let's see the demo. Here we can first go So we can use this command to just to enable the RAM ops the tracing function tracing. Then we can use the command to enable the watchdog. So in this kernel, I write the driver to delightning to trigger the bus hung issue. So we can see that the system can have no any response. We can see on the right side that when I execute this command, actually it's called this function. It will to disable the CCI bus clock. So the CPU is alive, but the bus is disabled, so the system is hung. Maybe wait 1 millisecond. So after the second time that we have the kernel have put up, so we can to mount the RAM ops virtual file system. So we can see in the virtual system, we have two entries. One is for the console. This is the dump log, and this is function trace, the log. So we can read out this file to get to know the execution flow. So basically that, I need to use the SSH from my PC to the board. So we can use so finally we can see that I have every the function calling the flow in this file. So we can see that if we search, so we can see it here that this is the function calling information or corresponding the hung issue. But there are many function callings. So you need to reverse review one by one to find some of the hints, then finally to get the nodes. So this is the first one. Okay, so actually I also share some of this demo on the YouTube, so you can offline to check the video for the demo. So the second case is that if the CPU is dead, how to read the current CPU state. So for example, if there are CPU dead, is maybe the IRQ or FIQ is disabled, but the CPU is in the loop, for example, pulling some of the register. And maybe sometimes now we use the untrusted firmware, so maybe the hung issue in the firmware side, and maybe stuck for the access the external bus. So the dead CPU in this case usually it cannot to react to the SMP, the IPI interrupt to dump the backtrace. So we know that the Intel X86 the architecture they have an NMI, but for the ARM CPU usually we have no the NMI. So how to handle this case that JTAG actually we can use this, right? We can connect to the target, but we also can use the Linux kernel, more convenient method to read out the CPU state information. So in Linux kernel, we have the Coresight CPU debug, this module. This module, we can consider it as the enhancement feature for the lockup detector. because that we know that if the CPU is stalled, or it will rely on the IQ or FIQ to response and to dump back the back trace. So this means that every CPU or live CPU can watch other dead CPU information. So this is based on the CPU sample-based profiling extension. Before that, this is reminded by the McNiche. This is actually in right by the ARM architecture reference manual. In there have detailed information for the hardware design. So here is that one thing that every CPU will to save its last CPU value into the debugger unit. So there have no any cache issues, no any concurrency issues. So we can directly to see the PC value for our CPUs. So in this demo, that we can see that when the kernel building, we need to enable the config Coresight CPU debug this module. Then for the prepared testing, there have two things we need to note. The one thing is that some of the CPU debug register is located in the CPU power domain. It's not located in the debug unit domain. So for this case, that we need to use the no hard to disable all the CPU idle state. Otherwise, you use this module also itself will introduce the hang issue. The second setting is that because the ARM CPU, if we have not enabled the IMI, but we want to use the CPU to detect the store CPU. So we also can rely on the RCU store to detect the CPU is stored. Then we can output the panic information. So in the panic information, we can read back the debug information for the CPU module, so can get to know the CPU PC state. Let's see the demo. So first thing we can enable the RCU panic on RCU store. So that means that there have RCU store, it will dump back the print out the panic, trigger the panic, and the panic information will to dump out the CPU debug information. So here we can to trigger one CPU lockup issue. So we can see actually now the CPU is alive, seems like, but there have one CPU actually is lockup. So this test case actually I write the code. So you can see that this case actually is that I disable the IQ in the kernel side. Then I use the infinite loop to let the CPU always run it here. So you can see that after the RCU store have detected the CPU store issue, it will to dump out the CPU state. So we can easily to get to know from the PCSR register. This is a live CPU to dump for this CPU 7 is the lookup CPU. So you can see that it can easily to get know that this CPU fall into the CPU lock, this function. So actually just now that function. So it can quite easily to find out the lookup issue. So the third scenario is that offline analysis the program execution flow. So basically that in a production that usually that it's in the manufacturing or in the customer, so the engineer is hard to access the production. So if we have some offline method to get back the trace data, so we can reverse the execution flow. There have another thing that we can use RAM ops. But RAMOps will introduce very heavily the performance downgrading issue, because it will to record every function calling in the software. So based on that, if we use the Coresight hardware tracing, it's just based on the hardware tracing data. So we can record the program execution flow with minimize the overhead. So basically the idea is that Coresight plus kdump, we can just save the hardware tracing data in the dump file. So, and we can rely on the crash tool to extract the tracing data. After we get the tracing data, then we can, based on the perf plus the OpenCSD to decoding this tracing data. So output the readable the program flow. Now, actually now this flow is smoothly can support the kernel panic debugging, but so far it cannot support for the debugging hang issue. So there have one tricky thing is that if the system hung, then watchdog or other method to trigger the SOC reset. When the SOC reset can preserve the Coresight RAM data, then we also can rely on this mechanism to actually attract the debugger for debugging the hang issue. So, for example, in the next time booting up, we can just to implement some kind of like the kdump flow for this case. So this is this demo, the brief the steps. So first thing that I listed here, the Coresight related modules and the kdump related options should be enabled first for the building the kernel. After that, then we need to prepare for the testing. So first thing that we need to enable the Coresight tracer and sync. So means that the Coresight hardware start to work. Then after that, then we need to enable the kdump kernel to know the capture dump kernel and the DTB. So after this step, then we can run some test case and the system panic. Because we just now have enabled the kdump with the capture dump kernel, so the capture dump kernel will to run in its own dedicated memory space. So this space will not destroy the previous panic kernel memory space. So we can based on that to save the core file for the previous kernel space. So offline, on the PC side, we have get the VM core this file. So this file have included the previous kernel memory, the space DDR content, also have the Coresight trace data. So we can use this file and use the crash tool. We can write some very simply the extension program to extract the Coresight dump the trace data. So after we get the trace data, we can base on the perf this command and base the kernel symbol list, so we can easily to get out the execution flow is readable format. So let's see the demo. Okay, so in my folder, I have prepared one folders. So you can see one folder is for the Coresight kdump initialization, another folder is for the Coresight kdump analysis. So let's first see the Coresight kdump init this folder. So we can see that this shell script it will to enable the Coresight tracing. And also it will to note the kdump capture dump kernel with VM Linux and the DTB. This is just the command. So the first part is for the info Coresight. The second part is for loading the capture dump kernel. Okay, so now, for example, we can trigger one kernel panic. So when we trigger this kernel panic, actually the Coresight kdump remit feature will save the Coresight related trace data in the DDR. So now this is the kdump, the kernel have ring up. So we can see that we can see it here that there have one file trace. This is proc VM core. This is just the previous that the kernel core file. So we can save this file in our PC for offline analysis. So this is that we can, for example, we can use the scp command to copy that the board, the VM core, this file, to our local file system, so I can save it. But because this need to spend much time, so I just to demo it here. So I just to use one previous the old VM core image. So finally, we can see that if we have the Crash2 and the VM core, VM Linux, so we can use the Crash2 to open it. So here I have write one extension for the Crash. So this extension is that like is a C code. Crash can support the Python or C program. So you can use this program to read out the memory data as you want. So for example, in my case that I need to prepare for the perf format compatible, the header, and also it here I need to read out the ETM metadata, and I also need to save the ETB or ETF related trace data, so combined to one perf format compatible file. So I can to load this extension. Then we can use this command, name the CS down to Coresight. Okay, so now we can see we have a new folder named Coresight dump. This folder. So we can see here have several different binaries. The first one is the Coresight trace data. The second one is the ETM metadata. The third one is the perf compatible format the data. So finally, we need to use the perf to decode the tracing data. So here we need to restart this the kernel, because that this time the kernel is the capture dump kernel, not the original kernel have the issues. So we need to run the original kernel, so we can get the correct the kernel symbol list. So we can see that we have a Coresight kdump analysis, this folder. So there I have the perf, this tool. This has been linked with the OpenCSD library, so it can decode the trace data. So just now here, this is on PC side, we have the perf.data, this file. So we copy it to the target, so we can do the analysis. So after that, then we can see this file has been saved in the board. So we can use the perf command. We can use the perf script command to print out the CPU ID, event, IP symbol, color symbol, and the symbol offset. And we can specify the perf data file name, and we can specify we import the kernel symbol list from the proc KO symbol, this proc node. So finally, we can see that after we use this tool, we can see that it can dump out the CPU before the CPU panic. What's the working flow for the reverse the program? Okay. So based on that, there have some follow-up with that you can extend this for your own SoC. There have two more things you can do. The first one is that if you on your system you have other master, you also can use the other masters to access the Coresight CPU debug module. Another thing that now we have enabled the Coresight kdump plus the Coresight tracing, this mass flow. So this is open source the tools, but we can also extend to for support the system hung. This case, for example, if there have other master in the SoC, so for example after the watchdog reset, the other master SoC can support kdump like the workflow to preserve the DDR and the Coresight trace data. So finally, we also can get one kernel core file, and we can use the crash tool and use the perf to reverse the executing flow. So all the patches has been uploaded to the Git server, and the RAM ops and the Coresight CPU debug module. This has been in the mainline kernel. Coresight for kdump. This is now working in progress. Just a reminder that actually this session is a continuous session after follow up our previous time. Previous time, Daniel Thompson have presented the kernel debug stories. So there are many technicals in one session. So this session wanted to extend with some of the live demo. So do you guys have any question? Yep.
So first of all, thanks for your presentation. And just one minor correction. So for Cortex-M, the V8M, so it also can support NMI now.
Oh,
Okay. So I just want to know for Linearo's regression test lab. So did you implement it to store the kdump or any panic information into the eMMC card? For example, if you want to run the worm reporter test for override, so you may have many panicers. So how can you, if the engineer is absent, so how can we restore the panic scenario? So can you give introduction?
You mean that the save the file in the Coresight to the eMMC or just in the bootloader to the eMMC?
Did you implement this kind of feature?
I don't think so, but I think that Akashi maybe have more. No. Okay. As far as I know, I don't know they have such kind of feature. Yeah.
Okay. Understood.
Is it doable? Sure.
Sure, it's doable. Yeah, it's doable.
In the last example, you moved the perf.data file back to your target.
Yeah.
Why?
Oh, we can do this on the PC side directly, but this means that the PC side we need to compare the perf with the liberf support, and we also need to import the VM Linux for the kernel symbol list. So for this case, I want to simplify it. For example, we just can use the on board. They have the KO symbol, this proc FS entry. So we can directly to rely on this to get the kernel list.
Perf archive exists and does all that work for you. It takes everything from your system and gives you a big tarball to take to your PC. Anything and everything that happens on ARM can be run on perf on an x86 box with ARM data.
Okay.
So I can work with you about the other stuff,
Okay.
like the libraries that don't exist or
Oh.
whatever.
Yeah. Have other question? Okay. So just the one slide. Quick. This slide have a lifetime warranty. So everyone here can send a question about today's session and suggestions for the future topics to support at Linearo.org. So Linearo member engineers also can access this email. So for any of the Linearo output support, engineers from the club and the core members are welcome to contact us to discuss how support and solution engineering can help you, for example, the training or the service. Yeah. It's just advertisement. Yeah. Okay. Thank you.